Welcome in the arena. My name is Allyson Klein, and today we've got a really exciting topic. I am with Carl Schlachte, CEO of Ventiva. And Carl, you've got quite a story to tell. Welcome to the program.
Thank you. Thank you for having me, Allison.
So, Ventiva hasn't been on the show before. So, why don't we just start with an introduction of Ventiva and how you came to head the company?
Sure. Okay. So Ventiva is a company that is in the thermal management business. Our goal is to support products that have thermal issues with a technology that we've developed that we call ICE.
Hmm.
ICE stands for Ionic Cooling Engine, which we can get into in a little bit. But effectively, what that is a small modular air mover that you can put in a spot where you've got heat. And that ability changes fundamentally the way people think about thermal management in a lot of modern electronics. So, and we can cover that a little bit later. But that's what we do. How I came to be here is about 14 years ago. I was brought in by the original owners of the company as a consultant to kind of figure out what was going on. And through a couple of twists and turns, I ended up buying the company.
Okay.
And so I've been running it ever since, and that's how I got involved initially.
Now, Carl, the reason why I reached out to you is I've been in the compute industry for a long time and I've seen different cooling approaches used to fans used in client PCs. Um, I've never seen your technology before and I wanted to have you on the show. Let's dive into the tech. What in the world is electrohydrodynamic airflow? And how do you see this changing the game from environments that have historically used traditional fans to cool hotspots in the motherboard?
So a couple things. First of all, the principle behind EHD has been known for probably since Faraday. So it's been around a very, very long time. There was initially an understanding of, in the presence of an electric field, you would get some kind of breeze or air movement off of it. We're the company that figured out how to take that and make it actually useful, scalable, and affordable. Because of that, that principle in physics that we're using, we can actually get targeted airflow into places that traditionally you wouldn't be able to get it into. So the differentiation between us and something like a traditional fan or a blower, and I just want to differentiate between those two terms really quickly because thermal people always get on my case about this. A fan is something like you might see in your bedroom, or a box turned on its side or something like that. When you turn that on its side and air comes in the top and out the side, it's called a blower. And those are the kind of things that are used in, for example, laptops, right? So
Sure.
it's still the same basic technology. What's going into those devices is there's electrical current that is turning a motor. The motor is attached to these plastic fins, blades, and those blades are shaped in a certain way such that when the motor spins, it's pushing the air. It's kind of everybody understands how that works. What we're
Mhm.
doing is effectively cutting out the middleman. We are using electricity to actually drive the air itself. And what that allows us to do is be very thoughtful about how that technology is actually deployed, because I can make it very, very small. I can get it into very, very tight spaces, both in thinness and in the types of areas that this thing goes. So if you think about a laptop, which we can talk a little bit about more if you want, um, in a laptop, if you pull open the cover and you look at it, you'll see two giant blowers in there generally. And
Mhm.
the whole purpose of those things being in there is to try to pull as much air through the system as possible in order to cool it. Our approach would be, where are the hot spots? We're going to put a little bit of air movement on that, and we're going to remove the heat directly on the spot that it matters the most.
Mhm.
And that changes the game for everything from laptops all the way through the kinds of stuff that we could do in servers, for example.
So that's where I was going to go next. How has the market responded to the technology and where do you have traction today?
Yeah. So the market has responded really well. It's taken us, I think, longer to get to market than we originally projected. We're not unlike a lot of startups in that sense. The difference being, the technology that we're replacing, the incumbent technology, blowers in this instance, have been around forever.
Mhm.
And the entire design methodology of laptops or, frankly, any computing device that uses a blower or a fan as an air mover has been designed and thought of as that is the method for removing the heat. So from the beginning of its design process all the way to the end, everybody thinks, oh, and here's where I put the fan. So
Mhm.
when we come along and say you don't need to use the fan, you can actually it's actually better if you don't, and you put in a separate technology that we call ice. We're also asking our customers to rethink the way they do things. And that cognitive leap, a lot of times, for somebody who's been doing this for 20 or 30 years, is, as you can imagine, a little bit more difficult than it would be if I was just coming up with a different fan, for example. Those
Mhm.
kind of things happen all the time. But for us, it is fundamentally different. And that requires a new way of thinking about how these things are done. The benefits on the other side, once you use it, are undeniable to the point where we have a lot of traction. But there's the upfront cost of getting people to understand it is probably a little bit more than we had originally projected.
Yeah, when I think about that laptop and you've described, you know, all of a sudden you're removing those big fans.
Mm,
That means that you've got incredible flexibility with what you actually do put on the motherboard.
mhm.
And you probably has a lot of benefits that come out of that, from a standpoint of user experience as well as energy. Can you just walk us through some of the benefits, that your customers are talking to you about that they
Sure.
think they can deliver from their system perspective?
Sure. So, a laptop is a great example to do this with, or to explain this with, because the form factor is something that we all know, right? The keyboard, the trackpad, the screen, the way things open, all that form factor we all understand. So, if you imagine underneath the keyboard, if I were to remove the keyboard, underneath that keyboard would be two blowers that in round numbers are 60 millimeters by 60 millimeters.
Mhm,
And so if you were to look at your keyboard, a good example would be to look at your keyboard and imagine that the size of your keyboard is the size of the motherboard in your system. Kind of close, but
yeah,
for illustration purposes, let's just stay with that. Now imagine I took that keyboard and I covered up 7,200 square millimeters of space on it. You'd probably be able to type on the R, the M, and the C, but nothing else, right? Everything over to the right and the left would be gone.
mhm.
And that is a metaphor for what the system designers are facing when they place fans or blowers in a system like this. That area is gone. Not only is it gone, it creates all sorts of other electrical problems for designers in the system that everybody just takes for granted. So, for example, if you imagine those two fans sitting there like that in underneath the keyboard, everything, all your IO is on the sides, right? You plug in your USB-C connector on one of the other sides, maybe you have HDMI, all the rest of it. All of those signals need to get routed to your CPU, and all of those have to go around the fan to get there,
Ah,
right?
okay.
And so as soon as we do that, we've created a very long path. We probably created things where we need retimers and these pinch points, and you need extra layers in the board for signal integrity. It gets actually pretty expensive. Fans are not cheap. To tell you a quick little story. I was in a meeting with some executives at a well-known laptop company, and the the VP says something to me like, why would I spend extra? We do cost a little bit more than a blower. Why would I spend extra on you? Fans are cheap. And I had to say to him, "Not really. I mean, look at what you spent to put a fan in there, right? You spent all this area. You spent time. You spent money in retimers. You spent money in cutting out hole. You're throwing away part of your board when you do this. You cut out holes to put fans in, right? Et cetera, et cetera, et cetera. And after we've taken them through it for a while, everybody's like, "Oh, wait, it's actually cheaper to use you on a total cost of ownership basis, and it's easier to get the design done." So this is why people start to pick up speed on this kind of stuff after a while.
No, it's fascinating, and, one thing that I'm curious about is what drove the innovation for the technology, and how did it's not like we haven't been working on laptop, cooling for a long time.
Mm.
How did the founding team develop this, and what was the inspiration for the technology?
The founding team saw a need for silent air movement. piece of this, I would say the main emphasis around this has been silence, and all true today, by the way. Everything I just told you about all the total cost of ownership benefits associated with using our technology have sitting right next to them this understanding that when you implement our stuff and get all those benefits, you get a totally silent machine. There is no sound of air moving through this thing. So I would say the original founding team was really fixated on air movement that also had silence associated with it. The thing that has happened over time for us has been that not only did we get the silence, but we started to understand things like modularity and size constraints make this thing super compelling in modern technologies because of the physical benefits it brings, in addition to the audible or lack of audible benefits it brings.
Mhm. Now, I'm sure mechanical engineers in the world all over the world are rejoicing. I wanted to go a little bit deeper with you. Your solution, I've been reading the tech specs, and it says that it's a confluence across the electric and plasma fields. And I want you to tell those folks who are not physicists in the room, explain what you're uniquely doing here and
Mhm.
break it down for us.
Sure. I and by the way, I do have to just to add this in. We've got some new mechanical engineers that have joined the company about a month ago. When you said rejoicing, it just made me remember this. It's like I went and checked in with them. How are you liking using our technology and designing this stuff? And
Mhm.
one guy actually said, "It makes me giddy."
Yeah. No, I was thinking back to the mechanical engineers that I used to work with at Intel, and just if I told them this, they would just be like, "Oh my god, this is gonna
Well,
make
that's
I
that.
can
Yeah.
actually design elegantly."
Yes,
It's
we get.
amazing.
Yes, we absolutely get that reaction. Okay, so let me try to give you the some of the physics on this. So the main part, the part of our technology that actually impels the air or moves the air, is effectively a very small wire. Okay, so just take whatever size wire you can imagine in your head, make it
Right,
really smaller than a human hair. It's
okay.
made out of a special material and all that kind of thing. What we do is we energize that wire, and when we energize that wire, if we do it right, a plasma forms around that wire, and the plasma is effectively just when if you were to stare at the sun, or actually the better way to think about this is when you in a total eclipse, when you see that corona, the crown,
Mhm.
which is another word for crown around the sun, that's a plasma. You're staring at a giant plasma, right? That happens in all electronics to some extent when you apply enough energy to it. So we apply enough energy to it, a plasma forms around that wire, and that plasma is a high energy field, and that field is reacting with the air that it's sitting in. So in the air are oxygen and nitrogen molecules, and what's happening is the plasma is interacting with the air. It's stripping ions out. Ions are positively charged. It strips an
Mhm.
ion out, and that ion is drawn across a gap in our device. The gap, there's an emitter and a collector. The collector is on the other side of the emitter. As that ion moves across that gap, it's just like billiard balls. It collides with other air in the space and imparts its momentum. And so if you keep that reaction going long enough, you get air movement. That's effectively how it works. The things that are super interesting about it, one I already mentioned, it's totally silent. Two, it's instant on, instant off.
Oh, yeah, sure.
Right? It's controlled by electricity, so it's like a light switch. You get instant air movement, and then it's off, right? If you want to. The other things that start to happen with it is because it's an electrical field and we have it attached to our version of electronics, we can monitor everything that's happening in that space. So we can, and in fact, we're working with folks on this now. We can tell device manufacturers almost down to the individual particle of dust how contaminated their air is, and that allows us to then say and do things in the system that create a better user experience, for example. So you could have a device that says, "Oh, you seem to be in a dusty environment. Would you like me to slow things down a little bit so you don't pull as much dust into your system?" Things like that. We can do all sorts of things like that. In essence, what we are doing is impelling the air directly through energizing the air.
That is so cool. That feels very Star Trek, Carl, I've got to admit. Um Are there unique aspects of your design that address things that a lot of folks are thinking about lately, like circularity and increased energy efficiency?
Yes, we support you know, all our materials are green, all, it's fully recyclable, all of those kinds of things. We actually we developed the entire technology under the auspices of, if you can't buy a component from here on in electronics distribution land, it doesn't go on our in our
Wow,
system, right?
that's
So there's
amazing.
nothing super special about it. It is under software control. The product itself is actually really meant to be, placed in a system in as innocuous a fashion as possible. So yeah, we do support all that. It really is largely design dependent, how our customers want to use it. We're giving them a thermal subsystem that they can implement it in their own way.
Now, I noticed on your website that you said that your current technology scales to 100 watts. What are the impediments in play here that would gate you from scaling beyond that threshold?
Okay, so let me first define my terms.
Mhm,
So when we say 100 watts, we're really because I would say the vast majority of our effort right now is in the laptop space.
mhm.
We're really talking about a heat measurement here, right? Or how much heat is being dissipated in the system. So when we say 100-watt system, we're talking about CPU and everything else that's in it. And what we're doing with our device is in those systems is we are using our devices are designed to be like effectively like Legos. In other words, there's one air mover of a particular size. We have other air movers of other sizes. You can mix and match them. You can stack them on top of each other. You can sit them next to each other. You can angle them. You can do all sorts of funky things with them because of the modularity associated with the
Mhm.
device to get cooling in a particular spot or air movement in different directions. Okay. So as we put this entire system together, we can then start to say, okay, we're trying to this is a gaming laptop and it's going to be at about 100 watts TDP. We're going to need this many ice units in order to be able to cool that, and that amount of air movement should be enough to cover the heat bill, as it were. What 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 scales this technology up and further is our ability to make these each of these devices more modular and increase their performance. So we do have a roadmap that says that we increase airflow for unit size, and just like everybody else has a roadmap. And so the third generation parts can push that up, but yet beyond 150, maybe even to 200 watts.
That's very cool. I can't wait to hear how you go. I only have one more question for you, Carl.
Sure.
Um, what's next in terms of how we're going to see this technology emerge in the marketplace? Any forecasts of what's coming next from Ventiva that you're comfortable sharing?
Sure. So a couple things. What our experience in laptops has taught us, laptops are honestly maybe the most perfect petri dish for thermal technology development as you can get, because they're small, they're constrained, it's a highly commoditized market. So you got to work on cost, you have to work on utility. There's a whole bunch of things around it. Like if you get your story right, if you can get designed into laptops, you can pretty much win anywhere. What that means for us is we can then start to look at alternative markets that have heat problems in areas that aren't satisfied by just blowing a metric ton of air through the thing. When I say a metric ton of air, my mind, I don't know about yours, immediately moves to things like servers, moves into areas like the data center, the tower sitting under your desk that might be rendering something. There are there are dozens of spots in those machines where if you just had the ability, I'm just going to give you a couple examples. Let's just say I've got a blade in one of my servers, and because I'm moving air from the front of that to the back, to the back generally. The air towards the back is actually hotter than the air at the front because it's already passed over a bunch of components that are throwing their heat back up into that air. There are dead spots in the back, and these are all, by the way, everything I'm telling you is not like a deep dark secret to the designers of these things. They've just had to put up with the fact that I can't put fans at the back of this machine. I don't have any space for it. So
Right.
if I could get air movement between, let's say, memory modules, I could reduce their heat and reduce bit errors and keep system uptime higher. If
Mhm.
I could remove 2 or 3 extra watts of heat from a GPU, I would have that GPU not throttle as much, if at all, and keep the cost, keep the utility of that machine up. That lowers its total cost, right?
Sure.
Eh, all thermally bounded systems throttle in order to stay below some level of heat, right? The ceiling of heat is predetermined. The job of the thermal designer is to keep everything below it. The problem most thermal designers have had is they do the static analysis of the system at its peak, or in different scenarios. They don't have any way of reacting in real time to what's going on. So I guess what I would prefetch for you is we like that market a lot, and
Mhm.
we like the idea of putting intelligence into thermal management in a way that makes the entire system run more efficiently using modular air moving components that are intelligent and silent in order to keep the entire machine at its peak performance. That's where we
That's
see.
that's amazing. I my mind is expanding into all sorts of different applications for this technology, and I can't wait to keep the dialogue going with you, Carl. For those who are in our audience that wanna engage with your team now and talk about different implementations, where would you send them, to find out more about the technology and to connect with you and your team?
So they can just go right on the website. We've got one page on the website devoted to applications, type work or general questions. They can put a question into there, and we'll get somebody back in touch with them and get it answered.
Well, thank you so much for taking some of your valuable time to talk to Tech Arena. Thanks so much.
Allison, thank you so much for paying attention to heat. Not many people do.